Hey everybody, welcome to today's lecture for robotics. Today's lecture is called Kinematics using the Jacobian. And as usual, we start off with something indicating why you should listen to me for the next little bit. So in the last lecture, we did kinematics, and what that allowed us to do is it allowed us to calculate the position of the end effector if we're given the position of all the joints, right? So given the joint states. Now, this is pretty cool. That was quite a useful thing to learn. But often when we're working in control, we care about the velocities of the end effector. So like if you picture something you're trying to do with a robot arm, perhaps you're trying to write a word or something like that, you might care about what the velocity of the end effector is, both in a linear sense, so meaning how it's moving through space, and an angular sense, so how it's rotating. Okay. So what we would like in order to accomplish this is some relationship between the velocities of the motors, which we know because we have sensors on the motors, and the velocity of the end effector. Okay? So if we want to control the end effector velocity, we want to do that by controlling the motor velocities, right? So we need some mapping between those two items. So it's very similar to what we had before, where we were trying to find a mapping between the end effector position and the joint positions, but now we're trying to do the same thing for the velocity. Okay. So some notation, we use v to denote the linear velocity and omega to denote the angular velocity, right? So angular velocity being how the end effector is rotating, and linear velocity being how it's moving in space. Okay. Now, you'll remember in the previous lecture already, we started using Qi to represent the joint state. Okay, so for every joint I, Qi represents the state. And borrowing some notation from physics, we'll say that Qi dot represents the velocity of joint I. Okay, you may have seen this notation before, but basically if we want to find the derivative of something, we just put a dot on top, or denote the derivative of something rather, we just put a dot on top. So Qi dot is the derivative of Qi, and so given that Qi is the state of joint I, Qi dot is the rate of change of state of joint I, or the velocity of joint I. Okay, so how do we do this? Let's take the example of a 2D two-joint arm. Okay, so we want to find some mapping that converts between the joint velocities and the end effector velocity. Okay, now what's really interesting is if you kind of picture this, right? If I said that there's a particular joint that's extending at 1 meter per second. So it's a prismatic joint, and it's sort of lengthening. It's lengthening over time by maybe, I don't know, 1 millimeter per second. I don't know, whatever is lengthening. What effect would that have on the position of the end effector? Well, the interesting thing about this is that there can't be a sort of global map for this, right? Because if that joint is extending and it's along the x-axis, then I would say my end effector is moving along the x-axis. But if that joint is extending and it's along the y-axis, then I would say that my end effector is moving along the y-axis, right? And given that joints can rotate, I could be anywhere between these axes, and that means that any extension of a joint or rotation of a joint will have a different effect depending on what my current joint state is. Okay, so what that means is that my mapping is actually a function of my joint states. Okay, so as it's stated over here, we're looking for some mapping so that we can calculate the linear velocity and the angular velocity of my end effector, and it must be equal to this mapping, which is a function of the joint states, multiplied by the joint velocities. Okay, so I want some linear transformation that takes me from my joint velocities to my end effector velocities. But that linear transformation can't be global. It's just not possible. It has to be a function of the joint state. Okay, does everyone understand why it's a function of the joint state? Oh man, I'm doing it again. I do this all the time in video lectures. I forget there's no one in front of me and I ask questions. But yeah, if there's some question about why this has to be a function of joint state, please message me on Discord. Okay, now this relationship, this function of the joint states that is a linear transformation allowing us to get from the um, joint velocities to the end effector velocities is called the Jacobian. Okay, so we denote the Jacobian function as j, q1, q2, and we see that if we just multiply it by the joint velocities, we get the end effector velocity. Okay, now just for simplicity for now, let's forget about the angular velocity. Let's talk only about the linear velocity. So the linear velocity is the velocity in space, sort of, not the angle of the end effector, but the position of the end effector, right? So if we separate that part out, we can say that v is equal to the linear velocity Jacobian, jv, which is a function of q1, q2, multiplied by q1 dot, q2 dot. Okay, now the shape of the Jacobian should be clear here because v, which is the linear velocity, is x dot, y dot, right? We said it's a two-dimensional system. So what we're trying to find is how the joint moves in this two-dimensional space. So we want its change in x and its change in y. And that's equal to this Jacobian multiplied by q1 dot, q2 dot. So the shape of the matrix necessary here is 2 by 2. Okay, and we're just calling the elements j11, j12, j21, and j22. So just to prevent any confusion, for now we haven't figured out what the structure of the Jacobian is. We haven't figured out how to get it. All we're saying is we want some function here. We want the Jacobian here so that it's the transformation that gets us from this to this. Okay, now how do we get those values? Well, interestingly, if we look at this relationship, right, we say the change in x, or x dot, is going to become j11 times q1 dot plus j12 times q2 dot. Okay, and similarly, y dot, or the change in y, is going to become j21 times q1 dot plus j22 times q2 dot. Okay, now if we sort of think about this, that's basically saying that j11 is sort of the extent to which a change in q1 affects or causes a change in x. And j12 is the extent to which a change in q2 causes a change in x. Right? Simply because that's how the linear algebra works out. But what's interesting about that then is that j11 can be thought of as how much a change in q1 causes a change in x. Okay, and we have a term for this. This is the partial derivative, right? So we are thus interested in the partial derivatives. j11 is the partial derivative of x with respect to q1, right? Because that means how much a change in q1 causes a change in x, right? It's the change in x with respect to q1. Similarly, j12 will be the partial derivative of x with respect to q2, and so on and so forth. Okay. So I hope that made a bit of sense. So let's say we've got some very simple 2D two-joint arm. Basically, at the origin, you've just got some joint that you've got a revolute joint, and its joint parameter is called Q1, and that's attached to a prismatic joint, which we call, which has parameter Q2. Okay. Now we can work out just from trigonometry that the x value of the end effector, so the end effector is over here, the x value of the end effector is equal to q2 cos of q1. Okay. Sorry, I've got a bit of a flu, so bear with me on that. So you can verify this, just play with the just check out the trigonometry, but x will be equal to q2 cos of q1 and y will be equal to q2 sine of q1, right? So that'll get me my x position and my y position. So if I've got these relations, then I can work out the Jacobian, because we've said j11 is the partial derivative of x with respect to q1, so you can work that out. j12 is the partial derivative of x with respect to q2, j21, and you get it, you get where I'm going. So what I'd like you to do is pause the video over here and try and work out these Jacobian terms, right? So I want you to fill in what is J11, J12, J21, and J22. I hope you all remember how to do partial derivatives. If not, please look for a tutorial or something. There's nothing super hard about it. Okay, so so if you've managed to work that out, well done. If not, like I say, just take a look online for some tutorial or something and come back to it. But basically, when we take the partial derivative of x with respect to q1, we're basically saying that q2 is some constant, and we're differentiating cos of q1. Q1 is only variable in our argument, in our statement. So cos of q1 differentiates to minus sine of q1, right? So this becomes minus q2 sine of q1 because q2 is our constant. J12, which is the derivative of x with respect to q2. Well, this is an interesting one. So because it's a partial derivative, q1 is a constant because we only care about the derivative with respect to q2. So cos of q1 is a constant, and so the derivative of q2 cos of q1 just becomes cos of q1. Okay, and you do the same thing with J21 and J22, and you end up with these Jacobian terms. Now remember, these were terms in the two-dimensional matrix, so we can shove them back in there. So if we look at this structure, we basically fill in the values from here in the Jacobian. Okay, so that solved for our linear velocity Jacobian. Now the angular velocity Jacobian is an interesting one. So the angular velocity Jacobian, we're trying to figure out how much the end effector is rotating, right? Now we've got two joints. Q1 represents the state of the first joint, and Q2 represents the state of the second joint. Now if Q2 extends or contracts, what rotation does that cause in the end effector? I want you to think about that. So if I've got basically a hand like this, and there's some rotation that's been applied in the past. Now if I extend or retract, what's happening to the orientation of the end effector? Well, nothing. Which is kind of cool, because it means that if we've got a prismatic joint, if we want to know what the angular velocity Jacobian is, it's just 0, which is kind of cool. Because basically we're saying that if I were to multiply J2 by Q2, I'd get the effect of Q2 on the angular velocity. And the effect of Q2 on the angular velocity it has no effect, right? So the coefficient should be 0. So J2 is 0. Similarly, if I have an end effector and I rotate by, say, 10 degrees at my elbow, right? If I rotate by, say, 10 degrees, what will change in the orientation of the end effector? Well, its orientation will also change by 10 degrees. So however much I rotate by, that's how much the end effector is going to be rotated by. So that's pretty easy as well. Basically what we're saying is that whatever the velocity of Q1 is, that's going to be the contribution to the orientation of the end effector directly. So J1 will be 1. Okay, so this J1, J2 will be 1, 0. And we can now combine the linear velocity and angular velocity Jacobians and end up with a full Jacobian. Okay, so now we can say this, we can come up with this expression, x dot y dot omega is equal to, and this is our full Jacobian. These are the terms that came from the linear velocity, and this is the term that came from the angular velocity, and we multiplied by q1 dot q dot. So the cool thing is we now have a way of converting the velocities in the joint angles to velocities in the end effector, okay, which is what we were going for the whole time. But there's something else that's important. So this, we now have this expression, right? We have the linear velocity and the angular velocity being equal to the Jacobian which is a function of the joint states, times the joint velocities, right? That means if we know the joint velocities, which we do, we can transform them to get the end effector velocities. Okay, so that's pretty cool. But often we actually want to do the inverse. We want to control the velocity of the end effector. So what that means is we will know the velocity of the end effector that we want. So we know the desired velocity of the end effector. And what we want to figure out is what joint velocities we need to apply, right? Because control is sort of the task of figuring out what to do about these q dots. Okay, we're trying to figure out what motor velocities or what powers we should apply to our motors. Okay, so we would prefer this expression, q dot equals j to the minus 1 q of v omega. And that's kind of cool because basically all it means is that if we wanted to do the inverse, if we wanted to plug in desired end effector velocities, we could just use the inverse of the Jacobian to get the to then get the motor velocities that we need to use for control. Okay, does that make sense? Let me just say that again because I'm not sure I was entirely clear. Basically, when we're doing control, what we're trying to do is calculate desired motor velocities. We want to figure out what joint forces to apply in a sense, right? And so what we're trying to work out is actually q dot. Now, how we work it out is by saying, well, what velocities do we desire to get on the end effector? Okay, and then we can transform that using the inverse of the Jacobian to back into the motor. So it's basically just this equation kind of restated using the inverse. Okay, but how do we get the inverse? Well, we need to invert the square portion of the Jacobian. So let's think about just the linear velocity for now again. So I don't know if you guys remember how to invert the matrix using the determinant. I certainly didn't. I had to look it up. But there's a formula over here. But in general, you're going to use something like MATLAB, which has an inverse function, or NumPy, which has linalg.inv to do the inverse. So you don't generally have to invert the matrix by yourself. You just use a computer and have the computer do it. Okay, but so what we had in the previous system when we were working in the forward when we were working in the forward direction is x dot y dot equals this thing, which was the linear velocity Jacobian times q1 dot q2 dot. And if we invert it using the structure, we get that q1 dot q2 dot equals 1 over minus q2 times sine of q1 minus cos of q1 minus q2 cos of q1 minus q2 sine of q1 q dot y dot, right? So that's we just followed this formula to get the inverse. And like I say, in real life, you'd most commonly use something like MATLAB or Python to find the inverse. Okay, but once you've got that inverse, it's pretty cool because now you can convert between desired end effector velocity to motor velocities, which means you can apply these velocities directly on your motors and you'll get this end effector velocity. Okay, so let's do an exercise. So you've got that same system we had earlier, and now we know that the current state of the arm is that joint 2 is extended to 3 meters and the arm is the arm is oriented along the x-axis. Okay, find the joint velocities that would move the end effector by 2 meters per second in x and 3 meters per second in y. So basically what that means is you've got your q2, which is 3 meters, you've got your q1, which is 0 because we're oriented along the x-axis, and we want to find the joint velocities. So that means we've got end effector velocities, so we've got x dot and y dot. Okay, so if we could, if you want to, you can pause the video and attempt to work this out, and it should be fairly straightforward. But I've got the calculation down here. Basically, all I've done is plug in values for q1, q2, x dot, and y dot, and we end up with a q1 dot and a q2 dot of 1 and 2, which we could then apply to our motors, and everything would work as expected. But there is an interesting thing about this, is that in practice, when we apply these motor velocities, we're going to change the joint states, right? That's the whole point. And if we change the joint state, that means the Jacobian changes, because remember, the Jacobian was a function of q1 and q2. So basically, as soon as we apply a motor velocity to get this 2 meter, 3 meter thing, our Jacobian changes. Our Jacobian becomes wrong, because now suddenly it's not sine of 0, it's sine of, I don't know, 5 degrees or something, because we've already rotated a bit. This coefficient becomes not 3, it becomes maybe 3.1 or something, because again, it's moved, right? So what that means is that we have to iteratively control our joint. We've basically got to, at every time step, we're recalculating the Jacobian, and we're then recalculating our joint velocities based on the new Jacobian. Okay, and what you'll find in practice is that you can end up with sort of wavy motion instead of straight motion. So if I tell a robot to draw a line, a straight line, something that just looks like this, right? The speed of my loop, of my control loop, will determine how straight it gets. So if the speed is not good enough, you'll find that it'll do this weird sort of cloud pattern, like bouncing almost, because I'm not recalculating the Jacobian fast enough, and so the line ends up being sort of a combination of arcs rather than a straight line. Okay, and that's the end of this lecture. Okay, I hope that was fun and interesting. I guess it was a reasonably short one. In the next lecture, we'll look at how to do this in 3 dimensions, and with lots of joints. Okay, thank you everybody for listening.